Hess's law states that when going from a particular set of reactants to a particular set of products, the enthalpy change is the same whether the reaction takes place in one step or in a series of steps. Okay, remember this is because Hess's law is calculating delta H, which is a state function. If the reaction is reversed, the sign of delta H is also reversed. If you double a reaction, you're going to double the delta H value. For example, look at this first reaction. We have xenon plus 2 fluorine yields xenon F4. It's negative 251 kilojoules. We'll compare that to the second reaction. What happened? We reverse the reaction. So what should happen to our delta H? It should become positive. So that's why we have a positive delta H now. Now look at the first reaction and compare that to this third reaction. What happened there? The reaction was doubled. So notice what happened to our delta H. It was also doubled. So remember, if you reverse a reaction, delta H needs to be reversed. If you double it, delta H is doubled. Here we have a reaction, and they give us the delta H of combustion for graphite and diamond. So we need to write our equation out. So we have graphite, and we're burning that. And so we should get carbon dioxide. Now we need to write our delta H for diamond. It should be the exact same reaction, except we're going to use carbon diamond. Okay, now let's look at our reaction. We have C graphite as a reactant. We have it as a reactant down in the bottom. We have C diamond, which is a product, and we have C diamond as a reactant. So we need to reverse that second reaction. When we reverse it, everything's going to get reversed. And what should happen to our delta H? It should become positive. We're going to scratch through this equation so we don't get confused later and accidentally add it up. Once you have your equations where you want them, then you can start crossing things out. If it's a product on one reaction and a reactant on the other, you can cross it out. Notice, once we've crossed out everything we can, we have the reaction that's above. C graphite goes to C diamond. So we add our delta H's up and we get 2 kilojoules. Okay, look at this problem in your booklet and pause the iPod and try to solve this question on your own. Notice we have boron as a reactant, we have boron as a reactant in the reaction, so that one should be good. That's the only place we have it, so we have to leave that reaction alone. Now, we look at hydrogen. Now we look at hydrogen and notice that hydrogen is only located in this third reaction. We want 3 of them and we want them as a reactant. We have 1 and it's a reactant, so we need to multiply that reaction by 3. So we multiply everything in that reaction by 3. And we multiply our delta H by 3 as well. Cross out our top reaction and make sure we don't accidentally add it later on. Also, the liquid for H2O is very important, so make sure that you use that. Now we need to find B2H6. It's located in this second reaction. We want it as a product, and it's a reactant currently. So we need to reverse this reaction. So we rewrite that equation while reversing it. Cross out our reaction at the top to make sure we don't accidentally add it later. So now we have all of the pieces of the reaction where we want them. So we can start trying to add. So now we can start trying to cross out the items that are as a reactant and a product in another reaction. So we have 3/2 oxygen, 3/2 oxygen. That adds up to give us 3, and we have 3 oxygen on the product side. But my waters, I need 3 waters in order for it to cancel out. So I need to multiply that whole equation by 3. So now I can continue to cross things out and make sure I am only left with the things that are in the reaction above. And now I need to add up my delta H's. So I have negative 1273 plus 3 times 286 plus 2035 plus 3 times 44. And that gives me 36 kilojoules. Notice in this problem we have SiH4. We want it as a reactant, and it's a product in that first reaction. So we need to reverse it. And when we reverse it, our delta H is going to become negative. Now we need oxygen, but oxygen's in 2 places, so I'm going to leave that to the end. Find my silicon dioxide. It's a product. We want it as a product, so we're good. We want 2 waters. So that last equation, we're going to need to multiply by 2. Because it's in the right location, we just need more of it. So now we should be able to start crossing things out and see if things worked out. Don't forget to cross out your reaction that you rewrote, just to make sure you don't get confused. Silicons cross out. Our oxygens add up, so we have 2 on the reactant side, which give us 2 altogether. Our silicon tetrahydride is there. Our waters are there. Everything else crosses out. So now we can just add up our 3 delta H values to get our answer. If we look back at the multiple choice values, that means A was our correct answer. So we're looking for delta H first off. We notice that calcium oxide is a reactant. We have it as a product down here. So we're going to need to reverse that reaction. Remember, when we reverse the reaction, delta H gets reversed as well. Cross out, make sure we don't get confused later. H2SO4, it's a product, so we need to reverse that one as well. So our delta H gets reversed. Cross it out. Now it's calcium sulfate. We want it as a product. It is a product. Correct number, so we leave it alone. Waters, correct number, correct location, so we leave it alone. Cross things out. Everything but what was in our reaction crosses out, so we were good. Now we just need to add up our delta H's. We get 754 as our delta H, but if you look up at the top of the problem, it says how much energy will be given off if we burn 56.08 grams of calcium oxide. So we need to find out how many moles of calcium oxide we have. And it turns out that we have pretty much 1 mole of calcium oxide. Looking at our balanced equation, 1 mole of calcium oxide gives off 754 kilojoules of energy. So plugging that in, kilojoules is our answer. So always read your questions carefully to make sure you know what the questions are actually asking.